All right, so in the last video, I talked about named entity recognition, being able to locate spans of text that refer to entities and classify what type of entity they refer to. And so now the second thing I'm going to talk about for lecture for class on Thursday is entity resolution, or also known as entity disambiguation. And so entity disambiguation associates named entities to a knowledge base. Like Wikipedia would be overwhelmingly the most common, but it doesn't have to be a Wikipedia. It could be any type of knowledge base. The term entity linkage refers to doing both NER and entity disambiguation, and this can either be done end-to-end or the two tasks can be done separately. An entity is a unique entity, so an entity that's been disambiguated. And a mention is text that we know is an entity, but we don't yet know which one it is. So a mention is a span of text that has been classified as containing an entity, but before we've disambiguated it. So why would we need to disambiguate entities? Well, first of all, entities can have many, many different aliases. So John F. Kennedy could be John Kennedy, could be Senator Kennedy, could be President Kennedy, could be JFK, etc. And just because there's a text string matched to an entity's name doesn't mean that it refers to the entity of interest. So we could have John F. Kennedy Airport, John F. Kennedy Elementary School, the John F. Kennedy School of Government, John F. Kennedy Street, other John Kennedys, Mrs. John Kennedy. This one is very common in our historical newspaper data. Lots and lots of Mrs. Husband's name. Of course, Mrs. John Kennedy could also be, Jacqueline Onassis, right? And so especially with women, it's also common to have them referred to with different names. There's John Kennedy Jr., etc. So if we were to just do a keyword search for John Kennedy and use that as a measure of how often some piece of text talked about John Kennedy, that's probably not going to be very accurate at all. And moreover, we might need the information that's contained in a knowledge base like Wikipedia or Wikidata for our downstream analyses. And so Wikidata contains this enormous knowledge graph with lots of useful information, like biographical information about these individuals that might be necessary for whatever downstream analysis that you want to do. So it could be extremely useful to take your biographical compendium or your data from media and get that linked over to Wikipedia and Wikidata, and that gives you a lot more information to work with. All right. And so there's a variety of benchmarks, but I'll say by far the most common one is Ada-Connell, which they manually annotated the Connell 2003 data set. So those are the Reuters news articles from 1997 and 1998, or 1996 and 1997. And this is the largest data set that's fairly high quality, and you'll overwhelmingly see this used. If a paper is going to fine-tune on a benchmark, it's probably on Ada-Connell. In these other data sets, I'd say that these are used mostly for evaluation. They tend to be smaller data sets. Actually, a lot of them do also come from news. Okay. And so before I delve into talking a little bit more about entity disambiguation, I want to make a note about entity priors. So if you think back to last class, we talked about how traditionally, like prior to DPR by and large, the standard approach to retrieval was to take the top 1,000 candidates from BM25, which is sparse similarity, and then re-rank their relevance. And the entity disambiguation literature took an approach that's quite similar in spirit, and you actually still see this done today. And so the standard is to take from 5 to 30 entity priors and only disambiguate against those. Interestingly, there's a 2009 paper that's pre-DPR that takes a bi-encoder plus re-ranking approach to entity disambiguation that's very similar to DPR. And they actually base it off of this other paper. This paper it came out of FAIR. And so a lot of people were kind of thinking in this realm around that time. And we'll see that this is going to be a fruitful approach. But let me say a word more about these entity priors. And so one of the kind of main data sets that people use to construct their entity priors is called a cross-lingual dictionary for English Wikipedia concepts. And it's a dictionary-like data set with English Wikipedia URLs on one side and short natural language strings on the other. And these strings are from English Wikipedia title, so the Wikipedia title corresponding to the URL, anchor text from English inter-Wikipedia links, so you'll have a link to that article and what's the anchor text for that, anchor text into English Wikipedia from non-Wikipedia web pages, and anchor text from non-Wikipedia pages into non-English Wikipedia pages for topics that have a redirect to English Wikipedia articles. And entity priors are constructed as the count of all links going to an article. And so this is an example from the original paper. So you see Hank Williams, and the highest prior is the page about Hank Williams, but then there's these other pages that come up when you search the text for a match to Hank Williams. And so there's an interesting paper in 2020 that is sort of obscure, but I think makes an important point. The entity priors differ a lot depending on which year of Wikipedia you use as a snapshot. So for example, in 2006, the most probable entity for the mention Amazon is the Amazon forest, and by 2016, it's the company. And depending on the year, the highest prior for Obama is the president versus Obama, a city in Japan. And so there's lots of examples like this. And you might think that especially for historical applications, doing something like this could have pretty poor recall, because whatever is kind of several most linked in Wikipedia examples of the text you're trying to disambiguate today might not be representative of the period you're looking at. So those temporality problems are going to make recall likely be bad. This is also going to be a big problem if there's OCR errors, because you're just looking for a string match to your entity mention in this dictionary. And if you don't find a match, then you might think that there is no match, or you might find a match to the wrong set of entities altogether. I'm also not aware of any framework using entity priors that allows for entities that are not in the knowledge base, which, say we roll entity disambiguation out to historical newspapers, there's going to be lots and lots of people, even in kind of highly reproduced articles that are not in Wikipedia today. And that might actually be an interesting outcome, who gets into Wikipedia and who doesn't. All right. So there are many different entity disambiguation architectures, and the punchline is going to be that a retrieval-based architecture that looks a lot like DPR is most likely to be practically implementable to real-world social science questions. But I'm going to show a couple of other architectures to give a flavor for how this problem can be conceptualized in very different ways. And I'll also give a warning that if you're reading this literature, you have to be pretty careful. If you go and look at the leaderboards, it's actually very easy to over-engineer to the unique features of the benchmarks and to the unique features of Ada Connell in particular. So to just give one example from a paper that I won't talk about today, but is another paper that I read recently, the paper claims to be SOTA for entity disambiguation on Ada Connell, which is the main benchmark. And as you read it, somewhere in the description, they say yes, and we also tokenize the first word of the text that the entity span is in. And if they don't do that, they're actually not SOTA. So you would think well, why? Why is that useful? And it's because these were articles scraped from Reuters. And so the first word of the document is the topic of the article, because that's the first thing that came up when they scraped Reuters. And So that you can see why like the topic of the article might be useful for disambiguation, but that's not like something that's likely to be in your data set. And that's just actually like a small example. But we'll see other examples where it's just very easy to over-engineer things to the benchmark. So I've been working kind of with a group of people to develop an entity disambiguation framework that's kind of a modernization of the retrieval-based framework that I'll talk about in a minute, and that also handles out-of-knowledge-based entities and is just much more practical to implement. And when we started this problem, the benchmarks are news. There's a bunch of papers on it, right? So you might think there would be something that we could just take and use it and maybe fine-tune it, but that would work reasonably well. And we found that actually that's not the case. And in part, I think that's not the case because it's very easy to over-engineer things to the benchmark. And so that's just a word of caution. All right. So the first model I want to talk about is Luke, and this is from a 2019 paper. Luke models entity disambiguation as a language modeling problem, where you mask mentions and predict the entity ID that they correspond to. So you can see here, the input text is Messi played in the World Cup, and so you're going to pass that kind of through the transformer, and then you're going to have these blocks that are appended to it that contain your entities, and you're going to mask some of those entities. And you're going to train the model by having it predict the Wikipedia ID of the entity that you've masked out. And so they use a large corpus where disambiguated entities are already identified from Wikipedia. And both words and entities are treated as the input tokens, as we saw in this graph here. And entities are randomly masked, and the model is trained to predict these. And essentially, it's trained just like BERT. They use BERT large as the base model and train the model to learn what the unique identifier is based on the context. And then at inference time, the model disambiguates mentions sequentially using words and already resolved entities. And they have a couple of different ways of doing this. They find that starting with the entity in which they have the highest confidence first works best. And so in a figure, you see Messi played at the World Cup, and now it's inference time, so they're going to mask both Messi and World Cup. And then they're going to predict the most confident entity. And then they're going to pass that through again and predict the other entity. So this is state-of-the-art on one of the papers with code leaderboards for entity disambiguation. But when you dig into it, there's various reasons why modeling entity disambiguation with a masked language model isn't a practical solution, I think, for real-world problems. So Luke limits to the most mentioned 50,000 entities in Wikipedia. And so you can only predict an entity to be one of the most 50,000 mentioned entities in Wikipedia. Why does it do that? Well, we talked about this when we were talking about multilingual language modeling. It's because taking a softmax over a large number of entities is computationally intractable. So there's something like 13 million pages on Wikipedia, and it's limiting to the 50K most common entities. Actually, if you look at the most mentioned entities on Wikipedia, they're disproportionately things like locations. And so actually the most mentioned entity on Wikipedia is United States, maybe not surprisingly on US Wikipedia. And so you're pretty unlikely with only 50,000 entities to get good coverage of entities for most applications that may interest us as social scientists. Also, it can't handle entities that are not in the knowledge base, which are likely to be common in practice. You might have some documents where you're confident it's only talking about people in Wikipedia, probably not top 50,000 people in Wikipedia, but in practice, it's very common in any documents you have to have some people who you'll be able to disambiguate to Wikipedia and some people who aren't in there. This also only considers the 30 highest entity priors. And so it's using kind of that first stage entity prior rankings that we talked about. Okay, so that's the first approach, which is the masked language modeling approach. Another approach is autoregressive entity retrieval. So this approach is entity disambiguation as a machine translation problem. And it uses a transformer seek-to-seek architecture to generate entity names. So the seek-to-seek architecture is BART-based. And so essentially you're going to translate the mentions of the entity into their Wikipedia, into their knowledge base ID. And there's a concern that this could generate non-valid entities, and so they do a constrained decoding that forces each generated entity to be in a predefined candidate set. So you would translate President Kennedy to the Wikipedia page, to the Wikipedia entry, John Kennedy, President of the United States. All right. So the challenge of this in practice is that seek-to-seek transformers, as we've seen and we'll see again, take a lot of compute to train. And there's other work pointing out that this approach is very, very compute intensive. Autoregressive generation of tokens can also be costly at inference time. And then finally, constrained decoding requires you to know the full set of entities that could appear in the text ex ante. And in many practical applications, the whole point is that this is not known ex ante. All right, so now we've seen the approach of mass language modeling. We've seen the approach of seek-to-seek transformer-based translation. And now I want to talk about entity disambiguation as retrieval, drawing on a model called Blink. And just so you can see here, my kids really enjoyed a ride in the Jaguar. So it's going to embed that text, and then it's going to look for nearby entities in Wikipedia. So this is going to be like a re-ranking strategy. It could be like the 100 closest entities, or it could be, the 100 closest pages or pages within a certain distance. So Jaguar is a junior roller coaster, Jaguar is the luxury vehicle brand, etc. And so it's going to get the closest entries in Wikipedia, and then it's going to pass them to a cross encoder. And so, basically this is very akin to DPR. This model actually predates DPR and was in turn inspired kind of by another bi-encoder framework. And so basically around the time of DPR, there were a lot of people thinking about this, and the Blink authors were also largely at FAIR, and there's some overlap between the Blink and DPR authors. And so there really are parallels there. So what are the details? The sentence representation is the class token from the last layer. This is kind of before Esper found that you're better off representing documents as the mean average token representation instead of using the class token. The distance measure is just the dot product like we've seen before. What are the batches for training? Well, there's a one positive pair in each batch. Random negatives, so there's multiple randomly sampled negative pairs. And then hard negatives are obtained by finding the top 10 predicted entities for each training example. And these and they add these hard negatives into the M batch random negatives. And so the loss function is variation on cross-entropy loss following this Humea et al. Paper that was an early kind of application of bi-encoders to retrieval, and they do inference with FAISS. Okay, so what are the challenges in practice? Kind of looking at some of the other papers that I mentioned, when they kind of criticize this approach, they say, well, there's no fine-grained interactions between context and the entity description. Although addressing this through late interaction would look identical to what we saw last class with retrieval. A large memory footprint may be needed to store the dense representations if considering a large entity set. In practice, I don't find this to be constraining. Like on a single 40 gigabyte GPU card, we were able to essentially fit 13 million, close to 13 million queries and 13 million documents. And so I think like in practice, you can fit a lot of embeddings onto a GPU card, and even more into CPU memory, which is usually even larger if you're doing this on a CPU. So I mean, that's something to keep in mind. you wouldn't want to do a large-scale retrieval problem probably on your MacBook Air. But in practice, we don't really find this to be too much of a constraint. And it does require an appropriately hard set of negatives. And I can talk a little bit more in class about how we found this to be pretty straightforward to address, and essentially taking the Blink framework and modernizing it and making it work better for practical applications. It is an older code base and an older model. And so you wouldn't, I think, want to start with the Blink code base. But when we finish like our version of this, there'll be a more modern code base that people can use. Okay, so there are also other entity disambiguation frameworks. And so, for example, I've seen entity disambiguation as question answering, or entity disambiguation on knowledge graphs, etc. Some of these architectures get very, very convoluted, and I think it's, again, like, it's not uncommon to see them be pretty overfit to benchmarks. There might be some architectures that I've not mentioned that are really powerful, but in general, we found that actually the retrieval approach works quite well, and it's very practical, even for very large-scale social science applications. Okay, so I want to say a word about out-of-knowledge-base entities. So the frameworks that I've mentioned don't handle out-of-knowledge-base entities, and you might think that in practice this is a big problem because, I guess in this literature they're not so much thinking about like obscure people, but for example, they mention biointech. And so you have a firm that's very obscure, and then it becomes very famous, and it starts getting mentioned all the time, and it's not in the knowledge base. How do you deal with that? And so this has received surprisingly little attention. There is a recent EMNLP paper for a model called Eden that addresses this. How Eden works is the model first trains on in-knowledge-based entities only using a bioencoder. And so it's essentially going to take the Luke bioencoder. And then it passes unknown entities through the first stage bioencoder, clusters the resulting representations, and then entities that are not in a cluster with a knowledge base representation are assigned as out of knowledge base. And so this is their model architecture figure. So first they're training on the things that are in knowledge base. And so the blue is the knowledge base text and the red is the entity mentions. And then they're putting the unknown entities through the bioencoder. And then they're going to do clustering and get a new representation for the unknown entities. And they find that this does pretty poorly on unknown entities, precision and recall like in the 20s to 40s, which really isn't great. They argue that it's just a really hard problem. So there's other firms whose names sound a lot like BioNTech, and they tend to be in the biotech space, and so their context on Wikipedia looks similar to the context in which BioNTech is used. So they just argue it's a really hard problem, and maybe you need a human in the loop. But with our framework, the development of this is still in progress. So I don't have all the results yet, and we're still kind of labeling some of our evaluation data. But so far it seems to work pretty well for us, and like a lot better than we were expecting. And we just do some things that are different. Like we do the clustering co-reference part in the first stage, and then do entity disambiguation. And in this paper, they're just taking Blink, and they argue it would be too costly to retrain Blink. But actually, we kind of essentially retrained a model like Blink on all of Wikipedia. And it wasn't too bad. It maybe took a couple of weeks to run on a single GPU card. And that seems to kind of make a big difference. And so I think that there actually are ways to deal with the out-of-knowledge-based entities. And if we finish our paper before the end of the semester, I'll upload something about it to the website so people can check it out if they're interested. All right, and finally, I wanted to say a word about entity co-reference resolution. So do multiple references to to an entity within a document or across documents refer to the same entity. And so the literature on this problem is really, really small compared to the disambiguation literature. But it seems inherent to treat this as a symmetric biencoder plus clustering problem, right? We essentially want to know if something's the same, but we don't know how many classes there are ex ante. So you remember kind of from various things that we've discussed in the course that how do we treat that? We train a symmetric biencoder to map representations of entities that are the same to similar vector representations and representations of entities that are different to different vector representations, and then we do clustering. And we're sort of doing entity coreference resolution as a first stage of training our disambiguation model. And we can talk more in class about why that can be helpful. So I just also wanted to briefly mention this problem because you might actually, for whatever reason, maybe you don't want to go to a knowledge base, but you want to just know which references in your documents refer to the same entity. And so you can use coreference resolution to do that. And that's all I have for the lecture. And I'm really looking forward to talking about this more in class on Thursday. So thanks so much, and I'll see everyone then.